well, first of all, thanks for having me. I'm really, really honored to be to be closing this conference. It's really a thrill and honor. And I'm going to show you some of the work that I do. And I'm going to start by giving you a passage from one of my favorite books. This is called The Glass Bead Game. It's by Hermann Hesse. Maybe some of you have read it. It's from 1943 or so. And it goes like this. A game, for example, might start from a given astronomical configuration, or from the actual theme of a Bach fugue, or from a sentence out of Leibniz or the Upanishads. And from this theme, depending on the intentions and talents of the player, it could either further explore and elaborate the initial motif, or else enrich its expressiveness by allusions to kindred concepts. It represented an elite, symbolic form of seeking for perfection, a sublime alchemy, an approach to that mind which beyond all images and multiplicities is one within itself. In other words, to God. So Hesse is describing, well, let me set up the context for you. So centuries into the future, Europe has become this sort of intellectual utopia where all of the people are basically, it's like a post-work society, or in some ways you can almost envision it's kind of a parody as such. And there's this province, as Hesse calls it, a province in Europe called Castalia, in which there's this boarding school, and the students there are singularly devoted to this game called the Glass Bead Game, which is described as this sort of ultimate synthesis of all human intellectual endeavors. And the game proceeds with players kind of taking turns moving these glass pieces around the board, making these deep philosophical analogies between the different sort of intellectual creative pursuits of people. So for example, a person might make an analogy between like a constellation in a night sky and the notes of a Mozart sonata. And lots of references to literature and humanities and music and so on. And now what's interesting about this is that Hesse never describes the actual rules of the game. They're just kind of like, you're just given an impression that people are making these sort of deep intellectual insights. And it's almost as though he's kind of hinting towards something which is, almost the essence of creativity itself. And, we can like debate, what the definitions of creativity are, but for me, I always think one property that's consistent is that you can't really formally describe creativity, right? It's this kind of, it's something that you can't express in rules fully. I was reminded a lot of this during the run-up to the AlphaGo Lee Sedol match. And well, first of all, I guess if you really love a book, you kind of see it everywhere, don't you? But for me, I was really, saw a connection between this and this kind of event that happened early last year. So maybe some of you were watching this. A company called DeepMind, which works in AI, they made an AI, machine learning algorithm, which was able to play the game of Go and beat the world's top-ranked player at the time, Lee Sedol. Now, I was kind of unfamiliar with Go at the time, but I learned a lot about it, and Go is kind of much more popular in East Asia, and it's a little bit analogous to the way chess is popular here. And one of the really interesting things about Go is the way people talk about it. So Lee himself said in the run-up to the first match, he said, "I will do my best to play a beautiful and interesting game." And that really, really kind of resonated with me, because I'd never thought like, well, I mean, who talks about, he didn't say, I'm going to compete with this AI and try to win. It's almost as though he was talking about being locked in this like creative dance with this AI, and he wanted to play a beautiful game. I will do my best to play a beautiful and interesting game, right? And it's kind of common to hear Go players talk about Go in this way. So you'll sometimes hear players in the analysis talking about their justification for certain moves. They'll say, I felt the board in this way. This is a common kind of terminology that you hear. It felt warm or cold, and these kinds of abstractions that you don't really hear so much in other kinds of games. And now the reasoning for this will become clear when we kind of compare it to chess, right? So I was a big chess player growing up. I was really into chess, sort of my Eastern European heritage speaking for me. And I can tell you right now, for those of you who are into chess, you know that no one talks about chess like this, right? No one says, I moved the bishop to f3 because I wanted to put the pawn in check or whatever. It's a very analytical game. You'll start to see people, talk about opening game sequences and in very analytical terms, right? Now, it's worthwhile to compare how deep AlphaGo was to Deep Blue. Deep Blue is the name of of course, maybe if you were around 20 years ago, you may remember IBM created an AI called Deep Blue, not to be confused with DeepMind. A lot of people in this field love the word deep for some reason. But basically, Deep Blue beat the world's top-ranked chess player, and it's worth comparing how these two games work. So in chess, right, both of them are examples of tree search problems, right? So you can imagine that every game is like a leaf or a node in a big expanding tree of all possible game sequences. And it's really, really large. It's impossible to search through effectively. And so you need algorithms for pruning the search tree and kind of getting rid of possibilities. Now, in chess, this works okay because there are only 120 orders of magnitude in the number of chess positions, which is 40 orders of magnitude more than there are atoms in the universe, right? Now, the way that Deep Blue worked is they got a team of something like 80 grandmasters together in the room who created this sort of expert function, this handcrafted function which would evaluate the position, the goodness of the position for the chess player. So it would take into account all these rules and heuristics, like how many of your opponent's pieces are in check and vice versa, and all sorts of heuristics along those lines. Now, this works okay for chess, but it couldn't work for Go because Go has yet another 50 orders of magnitude more possible games. That's an astonishingly large number, right? Like, it's almost unimaginable to imagine how many possible Go games there are. And I suspect this is why players talk about it in these mysterious terms. You know, you have to use intuition to look at a board position and kind of get an intuition for what the next move should be. Now, so how does AlphaGo work, and why is it so connected to creativity? Well, this is quite interesting as well. So if you can read about this in the Nature paper about AlphaGo, they used a combination of two neural networks. And I'm going to describe what these are in just a second, a little bit more what they do. But I'll tell you first how they work in this context. There are two neural networks. One is called the value network and the policy network. The policy network does this. It looks at a current game position, like a board state, and it predicts the next move. And it does so by being fed millions of games from human players in the past. And it has no knowledge of the rules of Go encoded into it, or even the objective. It just predicts the next piece. So that's kind of interesting, because it has no knowledge. Unlike Deep Blue, AlphaGo has no knowledge of Go encoded into it. And the value network replaces that expert function that I mentioned before. It looks at a game position in the same way, and it outputs a score. And that score simply comes from analyzing many, many games, not even analyzing them, but just being told who won that game. So it has no knowledge of the rules of Go encoded into it, which is really interesting for me because, well, first of all, it's much more general as an algorithm. It can be used for many other kinds of contexts except for Go. But also because I think this is sort of the way we conceive of creativity. There's no rules in it. There's no formalisms. There's just kind of intuition built into it. Well, OK, so then, what are these neural networks, and why are artists and designers and creative professionals and all sorts of other people becoming very excited about them these days? So I'm going to describe them a little bit about how they work. OK, so neural networks are basically these machine learning algorithms which take as their input some data. Now, in this case, we'll look at images, right? And it detects patterns in those images. And then it combines those patterns into more complex patterns, and then combines those patterns into yet even more complex patterns, and on down the layers until it has this full, very high-level representation of the image. And the filters, or the patterns, may look kind of like this in the early layers, just really simple, few lines here and there, like gradient fields, things of that sort. But they become increasingly complex, and we can kind of see that complexity if we do a little real-time demo, as I'm showing you now. So here I have a live neural network running on my computer, and it's analyzing my webcam stream. So in the first layer, we have all these filters, like the kind that you saw before, and then for each of those, this is the responses. And so you see like there's some horizontal lines and vertical lines detectors. There are things that detect patches of common color, I think. There's like maybe... This one's interesting. Maybe it detects the stripes behind me. And as we go through the layers, it goes through these transformations, and in each layer, you get more complex patterns that are derived from the previous layer's patterns. So here you still kind of see me in there, but the patterns have become more abstract. They're not necessarily just like lines anymore. They might be things like corners or maybe cross hatches, things like that. And we do this multiple times, and at each stage, the patterns become more complex, and they become difficult for us to interpret even. But some of them are actually very interpretable, and I'm going to find you one that actually is quite interpretable, and that's my favorite. It's Conv 156. There it is. Seems to be a face detector, right? So if I put my face in front of it, it seems to like faces, right? And if I even block my face, it goes away, right? So that's what it's doing. It's gaining this sort of representation. Now, in the last couple of years, people have become more interested in what these are actually looking for. Like, what are these patterns, right? What's inside of them? And it's worth looking at these because this is actually kind of the seed for some of the artwork that has followed. So one experiment you can do that was kind of worked out a couple of years ago by these people in the research is you can isolate a particular neuron of interest, one of these pattern detectors, and put in a lot of images, lots and lots of images, and take note of the patches of the images, like the little subregions, which maximally activate that neuron. So like which excite that neuron, whatever that pattern it's looking for, it shows parts of the image where it's particularly present. And in the first, you can see here in this first cell, these are actual images or patches of images, right? Just a few pixels. And you can see that this one seems to like kind of diagonal lines at this angle, roughly. And this cell likes patches of images that show green, right? So pretty simple. But as you do this through the second, third, fourth layers, it becomes more and more complex, right? So here, you see that this cell right here, this neuron, likes grids or lattices or fences, gates, things like that. This one seems to like wheels. This one, I see some like upper bodies. This likes text. This is one that isolates text. So that's pretty interesting. So you're seeing like more complex patterns emerge, which even though they have many different colors, a particular neuron responds to them, right? Okay, so let me show you some art stuff that I've been doing the last few months that kind of builds on top of this, right? So instead of now sending a real image to the network, what I want to do is synthesize an image from scratch, which will have some properties. So for example, if I want to maximally activate a particular pixel or a particular pattern detector, what is the image that would best do that? So check out this animation. I'll describe how it works, right? So here what you're seeing is the process of synthesizing an image which maximally activates a particular neuron in the network. And the neuron is looking for things that look, I don't know, maybe like apples or something, or orchard. I don't know, however you want to interpret this, right? And it's an iterative approach. So what happens is that at every iteration, we start with some random image, or like maybe just a blank canvas, and we analyze it with the network. And then what we do is we calculate what's called the gradient. And the gradient, in this context, means the difference in all of the pixels that needs to be added to the pixels in order to make it excite that neuron more. So you do this iteratively, over and over and over, until the image converges onto the particular particular thing that it's maximizing, right? Now, this is a really neat trick that you can do for basically all of the neurons in the network, and there's a lot of them, right? And it's cool to look at them through the layers as you go. So in the first layer, you see that the features are very abstract. They're kind of very primitive, really basic, maybe just like parallel lines and kind of like, well, they're quite colorful, right? But they're pretty basic patterns. As you go through the layers, you see patterns start to emerge, and the patterns become increasingly more and more complex, right? And I'm just picking out some of my favorite ones. You start to see like almost, this looks to me kind of like hair. Right? And then as you go, you see like, I see trees here, lamps. You can provide your own interpretation if you'd like. But increasingly complex, right? So you have like building facades and domes and wings maybe and eyes and just entire object parts here. So you see here like kind of a wagon wheel or something like that, and the bird. And they're quite colorful as well, right? And this is just a sampling of some of them. Now, there are 7,500 in this particular network. This is called Inception. And I've organized all 7,500 of them according to perceptual similarity using this technique called t-SNE. And so the similar ones are grouped next to each other. So here you see like kind of some of the basic ones that are all grouped together. And if we go somewhere else, we have a whole bunch of them kind of that look similar. It's quite diverse though, so you don't see too much repetition, but you can see that there's just a lot of these, and I'm kind of slowly making my way through them. Okay, some more experiments. So here, this is a little trick here to basically synthesize two channels at the same time and combine them in interesting ways. So here I'm applying what I call a gradient mask. So at every iteration, I actually will take that gradient, the little difference in all the pixels that needs to be added, and I'll multiply it by a gate, like between 0 and 1. So on this, so there's two neurons here. One is like the flower, maybe flowers or something, and this one is kind of like domes or archways. And then here, I let all of the gradient for the flower neuron pass, and mask just cut off the gradient for this channel right here, the arches. And so you get only flowers. And then on the other side, it's the exact opposite. So you just cut off the gradient for this, and then only pass this one over here. Now, as you go towards the middle, I begin to add, I blend the gradients together. So in the middle, you get half of each one at each iteration. And what happens is, as it converges on an image, the network is forced to kind of try to find features that satisfy both neurons at the same time. So it's not the same thing as blending images. It's actually synthesizing images which have a trade-off between which of the two channels they want to satisfy. And so you start to see like kind of arch-shaped flowers or flowery-looking arches, depending on how you look at it. And you can do this in all sorts of ways, right? So here, I've taken 3 channels, and they're arranged in concentric rings. And it's quite interesting to look at the borders between them. So you start to see elements of multiple channels kind of like blending into each other. And sometimes they blend nicely, other times they don't. And you can just do this. There's endless of these. I've made like, I think, probably thousands of them, and because you can make them very cheaply. There's millions of combinations of them. And sometimes they mix nicely, but other times it's kind of like oil and water. Like here, these two don't like each other, and so they kind of just like negotiate for space, and they don't actually mix too much. Here I see kind of like a pattern like that as well. And yeah, again, like I'm just slowly making my way through these. I have thousands, so I'm not going to show all of them, but kind of like recently been collecting these and putting them online a little bit. Now, you can make video as well. So let me describe what's going on here. So it's the same thing as before, except now when I produce an image, I'll take it and I'll feed it back into the process. So instead of starting with random noise, I'll start with the previous frame. So it does this synthesis on top of the previous frame. And you can do all sorts of tricks. You can maybe kind of like zoom in on the image or crop it or maybe shift it. And there's all sorts of degrees of freedom of getting different kinds of effects. And so you're starting to see some of those here. And particularly, I'm riffing a little bit on techniques that were introduced by Mike Tycho, who's one of the researchers who worked on Deep Dream. Maybe a lot of you have heard of Deep Dream. That was kind of the really kind of along the same lines that was released by some researchers at Google a couple of years ago. And yeah, just like making lots of eye candy like this. So you can kind of like interpolate gradients over time and over space and make these weird Pomeranian faces. I love these. These are my favorite, I think. I use them everywhere, including in this one. Then another trick that I'm just recently started to play with is you can try to inject another image into it, and so it conforms to a particular, you kind of guide it to some shape. So if you blink, you might miss it, but that's a face blinking out at you. So nice way to make selfies, actually. So okay, so this is really like just kind of the tip of the iceberg, right? Because neural networks are really awesome at making what are called generative models. And generative models are probability distributions over image spaces. So you can basically take a data set of images and then generate samples from the probability distribution you've learned on top of it, and pull out samples that look like they came from the data set but aren't actually real. So this is some research from these guys, deep generator networks from last year, and you see that like how realistic looking these samples are. They're completely hallucinated by a neural network. So you see this is the art gallery. This is what you guys look like to me right now. It's auditorium, ballroom, dining room, kitchen, locker room, like all these kinds of things. And it's kind of really inside the uncanny valley, I think, a little bit, which is a really sort of neat thing. Now, one nice thing is that the researchers release their code, so every time that happens, lucky me, I get to play with it. So when they release their code, I use the code to generate my own samples on publicly available data sets, and you can see some of the results of that. So here you see boathouses and buttes. We have a lot of these in the western United States. And you see that there's a ton of variety in them. So like every time you generate a new sample, it's completely dynamic. The process is completely, in this sense, will generate a new one that's kind of realistic. And I really like the way people come out of these. So they're not optimized to make people, so that people come out looking really funny. I can't tell if this is a basketball or a head. And here in the golf course, it's just like a pair of legs playing golf. And then I think this is what I look like to you guys right now, right? Lecture room. Now, another neat property of generative models that was really introduced, especially by a class of them called generative adversarial networks, is this concept of a latent space. And each one of these generators, they take in a sort of input code, like a vector of numbers, which controls the high-level features of the outputted image. And different models have different ways of constructing this, but all of them share a sort of smoothness that's very consistent. So for example, if you find the latent vector which generates man with glasses, and you subtract from it the latent vector which generates man, and add the latent vector which generates woman, and then use that as the input to the generator, it will produce, lo and behold, a woman with glasses, right? So you can kind of see that. And so again, these authors, they released their code, and I started playing with it. And the first thing I did was I just used it to generate digits, handwritten digits. And you can see, like, I like to think of these as in between states of the digits are like digits that never came to being. They're like glyphs or characters that look like numbers but aren't actually, but maybe they certainly could have been. I used this for a project called A Book from the Sky, which I trained a DC GAN on a set of handwritten Chinese characters. So here you see that not only can you synthesize realistic-looking Chinese characters, but you can kind of play with this generative space as well and see like different variations of those characters that might come out of a neural network's brain. And you can do the same sort of interpolations between the characters. So here you see like eye, face, body. As doing these interpolations between them. Other people use these for things as well. So these are manga characters that were produced by the DC GAN. And then the author, Alec Radford, he actually made album covers. So these look like they came from a data set of album covers, like record albums and so on. So it's just kind of neat. And actually, the state of the art for this has gotten way better in the last year and a half or so. Now, just a few things from the research that I think people here will really want to be aware of because, like for example, okay, so this is PointCloud generation. You can make 3D models using these generative models. And you can see, these are just furniture. So I don't know if anyone designs furniture here, but you can melt, one piece of furniture into another, and you have this nice latent space to play with. And so this is kind of very relevant to people here because maybe you're a designer or you work with design software, Photoshop, Illustrator, and stuff like that. And you're going to see a lot more of these kind of coming into the software that you use on a daily basis. WaveNets are also quite interesting. So these are generative models for audio. These were released also by DeepMind last year. So listen to this. This is a jazz piano that's completely hallucinated by a neural network, which has listened to hundreds of hours of jazz piano. So it's really kind of the ghost in the machine, right? Natural language generation. So these are very relevant to things like chatbots and question-answer services and things like that. So this takes an image analyzes the image with a neural network, and then uses another neural network to produce language describing it. So again, done completely by itself. So it looks at this image of a beach, and it goes, "We were barely able to catch the breeze at the beach, and it felt as if someone stepped out of my mind. She was in love with him for the first time in months." It's trained on romance novels, by the way, that's why. So she had no intention of escaping. The sun had risen from the ocean, making it so on. Yeah, it kind of goes on like that. These have been used to make like screenplays, and people have made generative Twitter accounts, and just all sorts of like creative projects using natural language generation. And of course, it's very relevant. I'm a little bit of a practical joker, so I used it on top of deep dream videos. So here I'm captioning parts of this hallucinated deep dream stuff. So you see a small dog and a brown and white dog and a lot of dogs, basically, mostly dogs. The bus is yellow, a small dog, and so on. So yeah, just kind of as a joke, but I don't know, not really. Now this is the exact opposite. This is crazy, and this is just from a few months ago. Here you input natural language, and then it produces an image. So instead of image to text, you go text to image. So you go, this bird is white, black, and brown in color with a brown beak, and the generative model produces a sample which conforms to that description that you put into it. So you can expect a lot more of this in the next few years, and probably at a time that it reaches a maturity, you'll start to see it in a lot more of the software that you sort of interface with on a daily basis. It has its own nice latent space to play with as well. Okay, image to image translation. So this is a generative model which is conditioned on another image. It's a sort of like image to image network. And it can learn a generic image filter as long as you train it on a bunch of samples. So for example, if you're an architect, let's say, and you are always making designs for buildings, here's the windows and the window sills and the door and so on, you can have it automatically generate a realistic looking texture on your label map. Or maybe you can take the same thing for street view scenes. Like let's say you're making maybe a video game, right? Or you're doing stuff for self-driving cars. Or maybe you want to automatically take satellite imagery and get a map from it. Or even crazier, like a data-night filter. Just all sorts of examples, black and white to color, taking sketches and turning them into photographs and so on. Now, I used their software on a collaborative project during a workshop that I did last year in Milan. And what we did was we downloaded a whole bunch of satellite imagery and map tiles from Mapbox, and we trained a map tile to satellite imagery neural network from a few cities. So we could do this sort of city style transfer. So here what you're looking at on top is Milan. That's the map of Milan. And the red is housing, and green is parks, and so on. And then this is the actual satellite imagery of Milan. And then this is Milan in the style of Los Angeles, and Milan in the style of Venice. And it's kind of neat is that the roads have become canals in the Venice model. You can do this with you can just draw maps, right? You don't have to you can input anything you want into the network. So you can just make your own sort of fantasy islands, as I like to think of them. Another neat thing, this was kind of first proposed by this artist named Mario Klingemann, who works a lot with Pix2Pix, and he did this really neat thing where he took a whole data set of sketches of people from the 19th century or something, and then he trained a face tracker to face Pix2Pix model. So you can take one of these, wherever it comes from, and generate a face from it. And so I kind of adapted this idea in the following way, and it's a little creepy, but there's a reason for it, I promise. I took the State of the Union address, and I trained Pix2Pix to go from the face tracker to a generative model of the president's face, right? And so then I put myself in front of the camera, and then I could basically have control of this meat puppet, as I like to think of it. And I apologize, I know this is like really obscene, but it's worth looking at this and evaluating it, because actually just 2 days ago, this company called Lyrebird showed a video where they can convincingly imitate a person online with both their voice and their image. So in the future, you'll be able to generate media of any person, and you might be looking at evidence of yourself, like in a courtroom, being like, "That's not me." That's So this is all stuff that we should be aware of and thinking about. You can also, this is neat, because so you can run it in real time, and this is, I just kind of have this as a joke, because there's a point at which the person kind of disappears from the camera, and then what's left is, as you can see, as soon as you leave, there's a sort of just like a headless microphone and a suit and tie in front of a microphone. So yeah. Now, cycle again. This is the same thing as pix-to-pix, except it doesn't need the examples to be paired. So the authors released this crazy video of them showing a horse being turned into a zebra in real time, which is insane, right? And actually notice that every time the zebra passes in front of a pole, the pole goes striped a little bit. And that's because, like, yeah, well, it doesn't really know the difference between, it doesn't know where the zebra ends and the rest of the world begins, which leads it to make some really nice mistakes. And finally, the last thing you can do with generative models is style transfer. And this is something, I've been working with this technique a lot, and it's for the last 2 years, and it's come a long way. So this is called cubist mirror, as you can guess what it is. And actually, I have another style in here. I actually just installed this weekend as an installation at my friend's wedding. So I'm available for weddings, by the way. But actually, this is way faster now. So I'm running this in an old laptop, and you can get this at basically frame rate on a good computer. So really crazy stuff that we're doing with these generative models. Okay, I want to show you guys a quick demo. And this is something that I made with a collaborator of mine named Andreas Refsgaard. He's actually just across the water here in Copenhagen. And I'm going to show you what it is. I'm going to first, let's open up, sorry. Gotta put in the camera. So basically, this is a demo which is going to let me turn my drawings into music. Right, so here I'm going to open this again and open the Ableton set. Maybe some of you guys play with Ableton Live a little bit. This is music making software. And, okay, not too bad. So here's what I'm going to do. I'm going to draw pictures of musical instruments, and they're going to trigger clips in my Ableton Live setup. So here's Ableton Live. It's used to make music. And I have this camera, and now I'm going to draw a picture of a drum. So here's a drum, or something like it. So there it is. I'm going to hit classify, and it starts playing a drum. Right? So there it is in Ableton. So let's put in another instrument. I'm going to put in a bass guitar. There's my bass guitar. Yeah. How about a keyboard? And one more. Let's put in the saxophone. So we got our full jazz band. Oh no, it messed up, actually. It thinks the drum is a saxophone. And the saxophone, yeah. Okay, it's not perfect. It has its flaws. Maybe let's try that again. Let's get it right. Oh, there we go, okay. Bad angle, not bad. All right, let's try this. Let's just put in a whole bunch of these. Let it go wild. It'll count all of the instruments, and it'll trigger samples for all of them. So let's put in a few more of each instrument. Maybe just like a couple of drums especially. Yeah, and one more bass. How about that? Oh, my bass guitar is horrible, isn't it? Is that all in there? Oh. Okay, let's get it go wild, right? Yeah. Okay, let's switch gears. Now I'm going to do something a little trickier. So I'm going to get out of this, unhook this, and yeah, I think that's pretty good. Maybe like go a little wilder on the drums. Yeah, okay. I'm going to put a couple of effects in these, and then I'm going to control them in another way using another neural network. So here, I'm going to add another effect to this channel. Let's put in this, I really love this resonator. So let's put that in there. So what you can hear is now all of these, you hear this sort of resonance. And then I have this delay filter, so that's there. So this kind of controls, just for the drums, I have this sort of feedback. Let's turn that down. Okay, now check this out. I have another application here called Ableton OSC, which will let me control these from here. So watch, I'll check the tempo, and now I can control the tempo from here. A little fast. This is really slow. Let's kind of get to something normal. Okay. And I'm also going to select, on the return track, I'm going to select this feedback. So now I can control the feedback parameter of that, the delay pedal. And lastly, one more thing, the return, let's grab this one, and I'm going to select that resonator. And we're going to make this also, the dry wet is going to be a parameter. So now I can control the resonance. The effect is subtle, but you can hear it. And then here's the delay pedal, right? And the tempo. Okay, finally, Covenant Predictor. Now what this is going to do, I'm going to train a neural network to read my webcam and control those sliders. So here's how that's going to work. I'm going to add these 3 sliders, and now I can control those from here. Oh, really fast. Let's make it kind of, let's try this. Actually, no, let's turn up the resonator down on this. And I'm going to put my phone in front of the camera, and I'm going to record some samples. So now it's recording some samples. I'll go up to around 30 or so. Good, and maybe let's turn down the drums just a little bit. Those drums are crazy, aren't they? Now what I'm going to do is I'm going to change this to that, and let's make it go really fast. It's kind of more ambient now. And this, I had something before. I had like a bottle. I'll just use this pen. Why not? Put that really close to the camera. So I'll record this. So now it's going to kind of respond to the pen. Usually I do this with a bottle of water, but I forgot. And lastly, let's turn it down. I really like this as default, really low tempo. And that'll just be me. So let's record some samples. That's just me in front of it. It's my dubstep. Okay, so now I'll hit train. And it trains for a couple of seconds, and now it'll work automatically. Well, it kind of combines the two. Well, maybe it's not the most accurate classifier. There we go. Not bad. All right, let's kind of turn that down. Oops. Yeah. Okay. Another neat thing you can do, and this was done also by my collaborator Andreas, along with his collaborator Lassie. They made this basically playing video games by making sounds, and they just kind of they stole the show with this. I'm just going to play this video.
meh, meh, meh. Pew, pew, ay, pew, pew, pew.
Okay, yeah. Okay, so finally I want to talk about ML4A. So a lot of these materials that you've been looking at, they're actually part of a large collection of resources and educational materials that, along with some other collaborators and I, Andreas and Lassie and I, have been compiling over the last year, almost 2 years by now. And it's basically this free online book about machine learning for artists that contains resources, tutorials, code samples, and an in-progress book. And I'm just going to show you some highlights from all of them. A lot of it has grown out of these workshops that I've been doing. So over the last year or so, I've had something like 30 workshops, oftentimes with collaborators, sometimes by myself. And a lot of work has come out of that. So student projects, you're looking at some of them. And they've been all over the place. They've been at conferences and festivals and universities and companies and things like that. We're actually having one right here as part of the conference tomorrow. And lots of work has come out of it and fed back into the production of ML4A. There's this big collection of guides, which is tutorials and instructional manuals, something like 30 or so in total, that that show how to do all sorts of things, including the demos that we just looked at, among some others as well. And these are just highlights from some of them. So doing things like finding a path through image space. You see like this, Buddha becoming a dinosaur. So like how to find through a collection of images a path that connects two endpoints. How to do doodle tunes. So that was the musical installation that I started the demo with. And as well as making t-SNEs. T-SNE is this technique for taking high-dimensional data and visualizing it according to similarity. So these are all images that have been analyzed with a t-SNE of animals. And so you see like all of the whales have been put together next to each other, and you have lots of dogs over here next to each other, crickets and flowers and things like that. It is all done automatically. You can do it on your own images as well, which is a common workshop that I do. And there's software for doing so really quite easily. So that's all stuff that you can find here. Another one is an audio t-SNE. So here, these are drum samples. Right, so like you can do this with audio, you can do it with text. These are Wikipedia articles of political ideologies of sorts. So you see there's like a feminism cluster up here, and there's a nationalism cluster over here somewhere. There it is. Yeah, so this is a neat way that if you go online, I have this on my website where you can kind of browse Wikipedia in a nice sort of elegant way. And also I really love Wacinator, which is this amazing tool that lets you make art, music and art with machine learning. This was made by a researcher friend of mine named Rebecca Fiebrink, and it makes it really, really easy to get started, especially if you're a musician, to kind of get started with machine learning. And here you can see it's telling the difference between a coffee cup and a croissant, and then making music with it. These are just some of the projects that have come out of it, student projects, or projects by people who have used ML4A materials. This one over here in the top left was actually made by a student at Copenhagen Institute for Interaction Design at CIID, and it basically lets you turn appliances on and off, made by Bjorn, and others that were made by students of mine in New York and in Germany and so on. And I don't have enough time to do any of them justice, but they're all really clever sort of art projects that have come out of the materials. I also have Python data science guides, so for people who are more interested in the academic approach to machine learning, this is kind of a good starting place. So this is all Python code that you can do things like reverse image search. I have too many slides, I'm sorry. But basically things like object detection and running it on live TV and doing sort of, having fun in that sense. And my classes, I've been recording classes and putting lectures online, all of them freely. And so you can find those under this site, and they kind of, everything that I'm doing, if you want like a 16-hour version of it, this is the place to find it. And it just tries to make this subject as approachable as possible and to get started with. And finally, a book. And this is kind of the most behind aspect of it. I've been very slowly writing this. And it's kind of meant to make the topic and the science and the math as approachable as possible, as accessible for people as it can be. And it's kind of like a gentle introduction to the math of machine learning and how it works and applications and so on. So yeah, that's all I have prepared for you. If you're interested in this, please do come and talk to me. And this is also open to contribution, which I'd be very happy to hear if you're interested in. And I will do my best to play a beautiful and interesting game. Thanks.